Hello, this video is an extra to my series on the particle in an infinite square well. So in this video we're going to quickly look at shifting to symmetric square well potentials from a normal infinite square well, which we had in the previous video. Okay, so in my other series we looked at a simple normal infinite square well, okay, and we gave it some conditions, okay, which we state here. Now in this video what we're going to do is look at symmetric square well potentials. Okay, so what that means is that the square well is symmetric around the origin, okay, which we have here. So our potential goes to infinity where x is less than minus a half a, okay. A was this point here. If we halve it, we get this because we're symmetric around the origin, okay? Our potential is 0, where x is between negative a half a and positive a half a, and our potential goes to infinity, where x is greater than a half a, okay? So you can translate from this new square well to the old one by adding a half a, because we add a half a to this, we're just going to get a. Okay, so this is all around the origin, it's symmetric, okay? So this means that you can write the wave function for the new square well in the equation as the following. So, you can rewrite it. So, if you haven't seen my other series, we derived the wave function for the particle in the infinite square well. Okay, and what we got was we had psi of x was equal to 2 over a to the power half, so you just take the square root, okay, and then we had sine of n pi x divided by a. However, x is now x plus a over 2, okay, and this goes to n equals 1, 2, 3, and so on, okay, because this is a symmetric infinite square well. Alright, so doing a little trigonometry gives you the following wave functions, okay, so what we get is we have psi of x is equal to 2 over a to the power half, and then we have cosine of n pi x over a. Okay, so the quantum states are important here. We have n equals 1, 3, and 5. This is because any other numbers, okay, of course it goes in the sequence, any other numbers not in the sequence will mean this will go to 0 and the wave function will not be appropriate for our infinite square well. Okay, just being in basic terms here, trying to make it as simple as possible. Okay. And exactly the same for sine. Psi of x is equal to 2 over a half sine n pi x over a for n equals 2, 4, 6, and so on. Okay, these are the allowed quantum states. Okay, and of course, any multiples of these of pi for sine will not be 0. Any other number in these sequences, sine will go to 0. Okay? Okay, there you have it. So, as you can see, the result is a mix of sines and cosines. Okay, the bound states are these in increasing quantum order. So I'm going to write them out. This is the bound states in increasing quantum order. So we have psi 1 x equals 2 over a half, okay, and cosine of pi x over a, because n is equal to 1, okay. Now when n is equal to 2, okay, we're looking at the sine. Sine 2 of x, okay, sine of n is 2, 2 pi x over a, Now we're going to look at n is equal to 3. This is the cosine again, so it's just alternating cosines and sines. Sine 3 of x is equal to 2 over a to the power half of cosine 3 pi x over a. Okay, and it carries on alternating, okay, for the quantum states. Alright, so note that the cosines are symmetric around the origin. Psi x is equal to psi minus x, okay, the cosines are symmetric around the origin. And then for the sines are anti-symmetric. Like this. Okay? You may know these in your calculus courses, but we're looking at quantum mechanics here, so it's in terms of the wave function. Alright, so there you have it. That is an extra video. Okay, we're looking at the symmetric infinite square well. I hope that helped, and I'll see you in the next videos where we look at reflection and transmission coefficients.